First of all, it's great to be here. My name is Hakim Weatherspoon. I'm a professor in computer science. I'm also the Associate Dean for Diversity and Inclusion for Computing and Information Science. We have a analogous position for college engineering. And then I'm also the Associate Director for Cornell's Institute for Digital Agriculture. These slides say initiative, but recently it's changed to institute as one of the radical collaborations under the provost. So I'm going to talk today about a software-defined farm and what that is. But first I'm going to introduce myself a little bit more. My background is in computer systems, so related to systems engineering in the sense that it's a study of trade-offs. So that's for computers. And in particular, I've done a lot of research within the cloud. So I actually wrote a paper in late 90s, 1999, that was published in 2000. And it was a precursor for cloud storage. That paper is called Ocean Store. That paper was recently acknowledged as a most influential paper award in 2018. And the reason is that people don't realize it, but at the time in 1999, Google was only a year old. Amazon did not have any data centers. They didn't have a warehouse for books. They were selling other people's books. And there's no such thing as the cloud as we know it today. And so this paper and line of work showed how you store an enormous amount of data, essentially forever, without more than your lifetime, without losing a single bit. And so that was then used by Amazon, Google, and Microsoft for their, at least initially, for the large data centers that they have today. And they store maybe a third of the world's information together in their data centers. So my research actually covers cloud networking, storage, and computation. So about a third of the world's bits on the network, internet, go through those 3 or 4 cloud providers. They store a third or so of the world's storage, and then they have millions of machines. So they have at least a third of the world's computation. And a lot of my work has gone to underlie that. My area really is in distributed systems, so it touches the storage, the computation, and the networking. So what is a cloud then? According to the National Institute of Standards and Technology, the cloud is essentially, I'm not going to read this to you, but it's essentially network access to, this says a pool of storage and computation. So it's really network access to a seemingly infinite amount of compute and storage. If you have a credit card and you can pay for to rent a virtual machine, then damn it, any one of these cloud providers will give you that virtual machine. And if you need 10,000, they'll give it to you. So it's network access to an awesome amount or seemingly infinite amount of compute and storage. And to a first approximation, we have actually realized that definition. Now, the promise of the cloud has been essentially that of like a utility where we pay for electricity and water and other utilities today. We're not so concerned about exactly where it comes from. In the same way, you're able to buy computation and storage today without worrying exactly where those machines are physically. And this has been used to really catalyze the technology industry. And in fact, your Amazon, Google, Microsoft type companies are each worth multi-trillion-dollar companies. That's 12 zeros. I mean, it's just an insane amount of money. And it's been used to revolutionize healthcare. The Affordable Care Act, in a large part, its medical records are based off of cost savings for the cloud, financial systems, scientific research, and in fact, society. So we're interacting with the cloud on a daily basis. If you're watching Netflix or you're playing a game on Nintendo or whatever, all this is hosted by one of these companies in the cloud. But what about the edge cloud? So the edge cloud is where you may not have that reliable internet access. The access may be intermittent. So a farm, for example, maybe in the rural areas, it may have intermittent connectivity, or may not be as prevalent as it is, in a city where you have gigabit per second to the cloud. So what about that edge? Okay, and so the key though is that the cloud itself has some risk to it. Um, you can easily have all your information in one of those providers and find out, like we did yesterday, that Google's now all of a sudden going to start charging us for our pictures. So if you're like me and have a couple terabytes of family photos and video, you're not going to have to start paying more for that. But so it's very easy to get locked in, and a lot of my research goes into how to prevent that lock-in. So you can use different cloud providers interchangeably. But another big part of my research, what I'm going to talk about here, is how to enable in some sense, the illusion that you have access to the cloud, even though you may be disconnected. So the computation and storage that it provides, you need to have some continual access, even though it may not be there. And we'll talk about this in the context of digital agriculture. So this now comes into software-defined farm. And I'll start by talking a little bit about CIDA, which is Cornell's Institute for Digital Agriculture. So the key of a lot of my research is how do we break that vendor lock-in so we can use any cloud provider interchangeably. And in fact, I have a startup. So part of the research that I've done has now turned into a startup company. That startup's called Exotanium. It was started about 1.5 years ago. And it's doing that exactly. It's making the cloud cheap and interchangeably to use. And here I'm going to talk about for the edge cloud and the disconnected operations, I'm going to talk about digital agriculture and a software-defined farm. Okay, so let's first start talking about this says Cornell Initiative for Digital Agriculture. It recently became an institute. It's now under the provost, and it's one of the 8 radical collaborations. And the key motivation here is that we want to develop a agriculture food system that simultaneously promotes good health, well-being, prosperity for the farmer, and environmental sustainability. And in order to do that, it's going to combine technologies that's not just in agriculture or food science, but also in engineering, computer science, business, vet school. And this is going to be then used to increase not just productivity, but profitability and reducing its impact on the environment. Okay, and so that's CIDA, Cornell Institute of Digital Agriculture, brings together about 100 or so faculty across Cornell, and they come across engineering, computing information science, business, agriculture and life science, like I said, 5 or so, and vet school, so 5 or so different colleges, with the goal of transforming agriculture for some of those goals that I mentioned in terms of nutrition and environment, prosperity, and the environment. So this then shows that we need this change. It is a urgency because we have, on the one hand, malnourishment or undernourishment of hundreds of millions of children on a daily basis. Estimates are 150 million. We have mismanagement of the land, where the arable land has reduced and may not be enough by some estimates to sustain the productivity that we need by 2050. We'll have 10 billion people by 2050. And so its impact on the environment is significant. And not only that, agriculture consumes 40% of fresh water, which is 70% of humans' consumption of fresh water. So its impact is huge. So if we want to look beyond 2050 to just 20, 60, 70, 80, when our children will be around, we need to do something about that now. So I'll talk actually a little bit about that on the right, which is how do we reduce our impact or usage of fresh water in agriculture. So in general, what we need is better ability to collect data, so sensors, um, better ways to analyze. There's been a boom in data analytics and machine learning and whatnot. Better ways to integrate systems. So this is where systems engineering comes in and integrate the data with some understanding, the analytics, and then some way of doing something about it, some actuation. And then we may need to create some better designs as well. And then finally, here, this mentions here the social impact. I have a grant with Phoebe Stengers and Stephen Wolf that looks at the social impact of a software-defined farm. So if you actually enable a farm with networking and sensors and analytics, and you're much more efficient and whatnot, how does that actually impact the farmer and the entire ecosystem? So we're looking at that as well. And so some of what we would like to look at in terms of these grand challenges over the next 20, 25 years is some what if questions that really push the boundaries, which are, what if we could increase the total factor productivity by 0.5%? This would be significant. This is what's necessary to feed the population, the growing population. Could we reduce our water, nitrogen, phosphorus use, or increase the efficiency by 50%? That's significant to, these algae blooms that we are experiencing here in Cayuga Lake are significant, and that's just one physical realization of high nitrogen and phosphorus in the environment. Could we reduce the fresh water consumption by half so that we are able to use and sustain that much more effectively? Crop loss is significant. So right now we overly spray fungicides and pesticides because if a farmer loses a crop, it could be devastating for their farm. So how do we strike that balance where we can reduce it, but still not reduce the fungicides and whatnot, but not reduce the risk of a crop loss? And then foodborne illnesses, we see recalls all the time. Can we reduce that significantly each year? So these are some of the grand challenges. I'll actually talk about that third one there, how to reduce the freshwater consumption. And the approach that I'm going to use is what I call a software-defined farm. I should put a note here that this comes out of the computer science research area where there's a popular approach called a software-defined network. And a software-defined network took the networking research and industry by storm. What it allowed you to do was you had these multi-billion-dollar companies like Cisco, and essentially allows you to take a Cisco router, put a interface on it, and then you can now configure it for your specific scenario. You didn't necessarily have to pay for a new, very expensive router in order to tune it for your job. In the same way, we're going to do that for a farm. We're going to take some of these approaches of sensors and analytics and actuation, and we're going to have a way of having general classes of them, but then finally tuning them for different environments. In particular, this software-defined approach is going to have a class of sensors. So think a tree, and then it's going to have a way to instantiate different types of tree, a maple tree, a spruce tree. It's going to enable, similarly, a class of analytics. Could be AI or model-driven analytics, but it's going to have a class of that can be instantiated for a particular problem or situation. And then we're going to use the cloud, both the edge and the broader cloud itself for the computation, communication, and storage. Okay, so then this then allows that class, that template, to then be specialized or instantiated for different situations: dairy, crop, specialty farms, large, small farm, farms in the Midwest, California, New York. So for different environments. It's also going to take into consideration that the connectivity may be intermittent or absent for long periods of time, and still enable this cloud abstraction in that. And also it's going to take use of some autonomous devices such as drones and robots and vehicles and whatnot. We're also going to take in consideration the community. This says that what we're doing for software-defined farm will be open source, so others can take advantage of it. But then I'll also take a look at the social impact. What's the impact on the farmer and all the ecosystem and stakeholders around the farm, such as the extension workers and the investors and whatnot. Okay, so this then is the software-defined approach, which is looking at it's a systems, in some sense, a very much a systems approach, because we're looking at the trade-offs in these areas via these templates, and we're able to then specialize or tune a solution. Okay, so then the software-defined farm approach combines the sensing with data and communication, with cloud and analytics, with actuation. And that then is a software-defined farm. If you look at a layered approach, we have the cloud, which is the basis of this. We then have local computation and communication as an instance of the cloud. Some way to interact with the system. So this is management configuration interfaces. With some, now we're able to then have some higher level objects that we can interact with, maps and weather and stuff like that. And then we have the AI and analytics and decision support tools. Okay, and then it's some dashboard and whatnot. So this then provides a slightly different view of a software-defined farm. We worked a lot with Microsoft, and so this takes as a base a Microsoft project called FarmBeats. So FarmBeats allows, they have third-party tools that allow for sensors. I'll talk about that in a few slides. Communication, and the computation and storage and analytics. It doesn't quite have the actuation. We'll add that in there as well. So we build this on top of the FarmBeats system from Microsoft. Okay, so let me give a few examples. So first of all, we have an example with the Mike Gore lab. And so with the Mike Gore lab, one of the things they're looking at is northern corn leaf blight. So here is a disease that can take out an entire crop, like we were talking about. And if you identify it early, you can then spray fungicide and avoid crop loss. If you wait too long, then you risk losing an entire crop. So what people often do is they spray, in some sense, early and often. So that's expensive to spray. It's also very negatively impacts the environment. Okay, so what we like to do is to reduce the people spraying, but not have anything that we miss. So such that you only spray when you actually need to, and you don't miss spraying, missing disease. So he actually has some drones that look on top of the canopy and a robot from EarthSense that goes underneath. They're able to take pictures at fairly high frequency. So you take these high definition pictures every half second, and then they analyze those. So what they do right now is they take thousands of pictures. They then bring the drone, fly it for half an hour. They bring it back, exchange an SD card, and then go back out and fly it again. So it takes days in order to do that, and then weeks to get those results back. Using a software-defined farm approach, we're actually able to stream the images to an edge cloud, do the analytics near real time, and then decide whether to apply fungicide or not, within the day or certainly within a day or two. Okay, and so that's significant here. So this then uses that software-defined farm approach for the sensing, that drone and robot or sensors. Data and communication, I'll talk about how we actually transmit a large amount of data. We actually use a very old technology, the TV spectrum. So TV now is digital, and it turns out that that analog spectrum has been released, and you can use that now, especially in a rural area. It's free to use, and you can transmit hundreds of megabits per second in the middle of a farm with no cellular towers or anything. And then you can do the analytics on the side, the edge of the cloud, and then you could do some actuation, such as applying fungicide in this example. Okay. Another example is the Abe Struck in his lab. So Struck and Cheng and Laxo and Yu and Cousteau came up with a smart irrigation control loop. And here they have a sensor, microtentiometer, right here, that can measure water stress. This is different than a moisture sensor, which essentially measures water in the soil. This measures the water potential in the plant. So you can actually measure and communicate with the plant with whether it's thirsty or not. And so they've done this, and they've actually, what you see there on the right is they then matched they've been able to measure the water potential and then come up with a model based off that then matches what they're actually measuring. So they can then use that to drive when to actually water the plant. So we have now applying where you have the sensor plugged into the tree. You then do some analytics to figure out, that takes in weather as well. Should we actually turn on the irrigation? And then you may actually turn the irrigation on to then water the plant optimally. This alone can reduce the water consumption by 40% for a lot of agriculture that where you have to irrigate. So in this case, it's apples, but you can think, almonds, and which is a huge amount of water consumption there. So in any case, there's a large number of, and grapes as well. So there's a large number of agricultural products that can use this to reduce the water consumption significantly. Okay, so this then uses, again, the software-defined approach where we have the sensors. We're able to communicate those sensors in the middle of the readings over the middle of the farm. You could use TV white space. Here, you don't need quite the high bandwidth that you did in the other case, so you can use another technology called LoRa, long range wide area network communication. And then you could do the computation on the edge clouds, essentially in a farmhouse, or in the cloud itself, if you have connectivity. And then the actuation here is turning on the irrigation, so they'll actually water the plant. Okay, and so this then is two examples of applying the software-defined approach, which gives you this feedback loop. And then there's also, as far as systems engineering goes, there's a set of trade-offs for each one of these to make what type of sensor to use, how you actually do the communication. I've mentioned a couple of those. Analytics, cloud-wise, there's different cloud providers, analytics, and then actuation. Okay, and then finally, going a little bit further with that example, we have now deployed a software-defined farm in a field experiment. So here on campus, we're using the Cornell Orchard, and I'll show a map of where this is right now. So, this is a map of New York, and Ithaca circle right there. And then we have campus right here, and you can see, the track there. Engineering quad is over here. So if it wasn't due to COVID, we would be talking in person right now, most likely somewhere in the engineering quad. The Cornell Orchard is across the street from the vet school. Okay, and then you can see within the Cornell Orchard, we have a field, and which essentially is a shack, but it provides power for the edge cloud, the computation, and some of the communication. And then you have the trees that are here. Okay, and so this then is a side view of some of what I've just shown, where you have the trees. I showed you a field there, You have sensors that would be plugged into a tree, measuring the water stress. You'd have then a number of sensors that would be plugged into a sensor box. The sensor box then would provide, they'd be plugged in via a wire right now. It'd be possible to do Bluetooth wirelessly, but then the sensor box would communicate with the edge cloud, which is essentially the farmhouse. And here we're using LoRa, which is that long range radio, to some sub edge, which essentially is that gateway. It provides an edge of communication to the field, and then also a conduit into the computation itself, which could be within the house, or in this case, we're actually doing the computation in the cloud itself. So this is using Microsoft Azure. We have a hotspot, so it's an AT&T hotspot that has internet access. And then we're able to do some computation there. We're taking in those readings using that model that I showed you a few slides back. We include water at the top here, the weather, excuse me, and then a decision may come down that says that we should actually turn the irrigation on. And then you can see that comes down here. This is a Raspberry Pi that would then actuate or trigger the actuation to turn the irrigation on. I should say this model predictive control was done by Fenchi and Abe Struck in order to figure out when to actually do that. So this is a great example of using the analytics as kind of a black box. For us, it doesn't really matter what the analytics actually does, but we need an interface to that analytics, and we can, depending on the problem, using a different analytics algorithm. Okay, so this then is a side view, some sense of a software-defined farm. You don't need to worry about exactly what's going on inside of the cloud itself. Let me show you a quick video so you can see deployment itself. And I'm gonna switch over. Okay, so this then is a video. So here you can see the apple trees. And this is my PhD student, Gluar. He has a sensor box here, so it's weatherized and ruggedized. And then you have a sensor that then is plugged into the tree itself, which you can see up there. There's a single apple. It's the end of the season. Due to COVID, we had to essentially wait. So the harvest has already happened. Here's another sensor as well. There's a moisture sensor within the soil there. You'd also have one plugged into the tree itself in the sensor box. This is a weather station and wind sensor right here. And then we also have, I guess, a third or fourth tree right there. And then they're going to show the irrigation. And so here you have where the irrigation would actually be turned on. The Raspberry Pi would control turning that irrigation on. This is the farmhouse. It's a shed, but it's you can see here the sub edge. That's what communicates with the farm itself, and then the hotspot communicates with the internet. Okay, so the sub edge essentially is a gateway between the farm and the edge cloud, which may be there locally or maybe the cloud proper itself. So let me go back. Okay, and so then you got a side view via schematic and then an actual walkthrough in the farm. And this is, like we said, part of the Cornell orchard. So what we're using right now is a hotspot to communicate with the internet, but that assumes you have a cellular tower. The rest of this is the campus and whatnot. if you didn't have a cellular tower, another technology that we are setting up is a TV white space. And so here, what's going on is a couple things about this. Number one, technology-wise, we have moved away from the analog spectrum of TV for 10 to 15 years now. And actually, it was Ranveer Chandra at Microsoft. He's a grad of Cornell. He's one of the people who worked on with the FCC, the protocol of allowing to use the TV white space. It's free to use. You just have to make sure that nobody else is using it. And the way to think about this is that each channel, like channel 2, 3, 4, 5, some of you guys are old enough to remember TV going off and, you know, the color bars and the Star Spangled Banner and then a white noise. That white noise is exactly what we're using to send to communicate. Each channel is 20 megabits per second, up to 20 megabits per second. So if I have 5 channels, channel 2, 3, 4, 5, and 6, then I can communicate at 100 megabits per second. And there's other ways to divide it up to increase the communication further. This also travels a great distance, many miles. So you can actually cover an entire farm in the middle of nowhere and have high speed bandwidth. And in fact, there's a question, I spoke about this yesterday about 5G. And the issue with 5G is that you need to have a higher density of cellular towers for 5G. It's already very expensive to roll out a lot of these cellular technologies to the rural areas. And what happens is usually right as they're starting to penetrate, we then move on to the next generation. So you don't actually see the same level of penetration in rural areas that you do, of course, in urban or suburban areas. So 5G is even less likely to be rolled out into a rural area anytime soon, if ever. And so what the TV white space allows you to do is to connect an individual farm, all the sensors within the middle of a farm. And you also may be able to, I ran a workshop where you may be able to, it's called Snap Together Networks. So you may be able to connect different farms together that as a community can provide high bandwidth. And ideally until you get to a source where you have a high speed internet connection to the internet itself. So TV white space, which is a very old, 100-year-old technology, may actually be a wave of the future, which is interesting. So this is what we're using. We've ordered some TV antennas to then connect the Cornell Orchard to campus, and then that's a path then to the internet, because then we can use the campus internet to get to the cloud. We also have some LoRa between those 0.8 and 6 there as well. Okay, and so the key here is I showed you a deployment using 4 trees. What happens if you actually had more of an average size deployment, 5 plus 100 acres or thousands of acres that you may see in Eastern Washington for apple trees, or even in upstate New York here. How would you scale this approach to that? So this is showing where you may have the S here are sensors. So you may have sentinel trees and sensors that essentially you'll use for an approximation for an entire set of trees that are in close proximity. And this allows you, to then deploy this in a scalable way where you can then have some level of precision and also some level of scale or cost, so that you can figure out whether you should actually turn the irrigation on or not. And then if you can actually actuate these irrigation individually, then you have a way of doing some fairly precise level of watering. Another thing is, depending on the scale and size of the farm, there are choices for different technologies to use communication-wise. So we may have I talked about a couple already. LoRa, TV white space, Bluetooth is another one. They all vary based off of range, power consumption, cost. So if we want this to last an entire growing season, then we have to be thoughtful about that. Another thing to think about range-wise and bandwidth-wise is if what I showed you in a few slides before, there is a sub-edge, essentially that link to the farmhouse or the gateway. If that can reach all of the sensors, then you're fine. If not, you may need more of a peer-to-peer or ad hoc networking or mesh solution. So in that case, each one of these sensors may have a sensor box with those, and then they may actually work in a peer-to-peer fashion. So this sensor box would communicate with that sensor box, and then it'd be passed along that signal until it reached the farmhouse. And I've actually done some work in ad hoc networks as well. Okay, so that then shows how you may actually scale this to a much larger farm. Hundreds of acres to thousands of acres is what it should be able to scale to. And then finally, in terms of the set of choices that you may have, since in systems, computer systems, system engineering, we're looking at the study of trade-offs. Here you have different types of sensors. I didn't show you how it breaks down, but there's controllers to the sensors. We did discuss about different communication protocols, LoRa, TV white space, Bluetooth. You may be able to set up Wi-Fi and use TV white space as a backbone. So there's different ways of doing that, how to actually optimize that. State of storage is a storage, locally on a PC or desktop, or is it in the cloud? Where do you actually do the computation, locally, like you said, or in the cloud? How is the irrigation set up? How do you model that? Power is a huge deal. Batteries. Do you replace the batteries throughout the growing season? Do you use more expensive solar solution? And then some of the irrigation valves and stuff like that. Okay, and then let me go. I think it's my last slide. Then we have here essentially what I've shown you so far is set up trade-offs. It's really a system of systems approach. And it's one that can be used to tackle fairly large societal problems applied in this situations to digital agriculture. So I've taken what I've done for, I guess, just about 20 years in distributed systems and in cloud. And over the last 2, maybe 3 years, started to apply it to digital agriculture, which has been fascinating for me. It's been a new space. My father grew up on a farm. I did not. It's been very exciting here at Cornell to start to talk to people in different areas. So we have, like I said, 100 or so faculty that come together on a fairly regular basis, and to have that interdisciplinary research, in this case applied to digital agriculture. It has a notion of responsible innovation, which is interesting. A lot of my students go off to Google, Amazon, Facebook, and you don't really think about responsible innovation. If you're off to Google, how do you make the search faster? It's not, you don't really think about the ethics. We're starting to think about that more, especially with AI. Turns out it can have some very adverse effects. And similarly here, we are applying AI and some fairly sophisticated techniques. How does that actually affect the farmers and whatnot? Our initial designs are for good, to better affect the environment, to increase productivity. But what about the farmer themselves and the entire ecosystem around them? And so, like I said, I have another grant that looks at that responsible innovation at the same time that we're doing the technology, which is something different than what I've done, which is usually you do it later on, but that's too late for a lot of situations. So, okay, with that, I'll go ahead and stop and say thank you. Also, I'll say that I have, as a result of COVID, one more guest that's here. This is my son who is here. He told me he enjoyed the talk. So his name is Yared, like Jared. But in any case, he'll be with me for the question and answer period. But thank you so much, and let me know if you guys have any questions.
Well, thank you very much. And the floor is open to questions. Anyone who has questions, please just unmute yourself and ask them. I haven't looked at the chat, but I don't think, let me look right now. There's nothing on the chat. So I think we'll just, it's a small enough group here. I think we can just unmute ourselves and ask questions. So please, anyone, go ahead. I have some, but I'm going to wait until other people have a chance.
Sure.
I was wondering about the, you know, it looks like stuff that would be really useful within the United States or developed countries, but I'm sure you're aware in this digital agriculture, there are probably a lot of people who are interested in farms in Africa where the, you know, the farm size is 2 acres or 2 hectares or something like that. So is this sort of thing, you think there are applications for it in those situations, or are those small farms at a significantly bigger disadvantage?
That's an excellent question. We're actually working with a company that some of you guys may know. It was an alum of Cornell called Hello Tractor. The founder is a guy named Jahil, and it's kind of like Uber with tractors. So he has these charts to show the number of tractors on the entire continent, which is interesting but crazy at the same time at how small number of tractors there are. So what they do is they actually have an ecosystem where they have fairly sophisticated tractors that you have financiers, operators, farmers, so an entire ecosystem. And you can essentially request a tractor for a couple of days and harvest, you know, what used to take hundreds of people, now a few people, and harvest in a few days. And it's turned out it's profitable for all of those people, the farmer, you know, the financer, the operator, and whatnot. And we are working with him slightly different. They want to keep track of that asset, the tractor. And it's offline quite a bit, but they also want to know what it was doing, why it was offline and whatnot. I have some other line of research in blockchain, so we can actually write it to a tamper-proof log, which is what the abstraction that a blockchain gives you. But it is actually a very good question on, you know, do you have reliable power? Do you have the expertise that you need in order to operate this? The extension workers are and NGOs are pretty good proxies of the people that may actually be interacting with and whatnot. So we've started to look at it a bit, but you're right. A lot of this is tailored towards or assuming the United States.
I guess I might quickly, Al, while you're doing that, Norm Scott, wonderful presentation, Hakim. You're, in some sense, illustrating the vision I've had for many years, coming from engineering and agriculture. And obviously, I know Tim Mount's on, and this is more a question that he would ask, I would think. Do you have any sense of the kind of economics that would be involved in putting together a system like this? Because obviously that will be key, whether in the United States or elsewhere.
Yeah, thank you. Yeah, we're starting to create that. I do have a systems engineering Ph.D. student. And then also we're working on this. I have some social science collaborators. So I don't have any numbers just yet to present, but we are starting to do some of the stakeholder analysis and whatnot, and some of the return on investment. I think that the key is that that's part of the puzzle. You know, can you make it accessible and affordable enough? The other part, though, is you know, the knowledge base. Who would actually install, maintain, operate this stuff? Is it an individual farmer? Is it an expert that maybe the community hires or whatnot? So there's different models for that as well that are quite significant. From what, farmers are a fairly independent bunch and like to be able to tinker and understand things. Does this now, affect that in some way? So in any case, we are starting to look at the stakeholders and trade-offs and return on investment and a lot of those comparisons. But that's a great question. Thank you.
So I have a sort of similar question, a similar vein, is that how are you looking into various things involving legal, ethics, et cetera? You mentioned them, but I'm just curious what is ongoing and what kind of people have you pulled together or hope to pull together in the future for those things?
Yeah, no, that's actually a question. So we actually submitted for a National Science Foundation Science and Technology Center. So these are your $25 million centers. And we have a submission called CROPS. It's in the final stages. So, God willing, we actually get it. We had a site review. What would have been a reverse site visit or whatnot. But it's called a Center for Programmable Plants, CROPS. And it essentially, asks the question, what happens if we could have a dialogue with the plant? And actually, there's a language that we decoded and understood, and we could actually communicate back and forth. And we do have, as part of that, public relations and some of the ethics, because even if on one side the ethics are okay, the public relations may not be. Somehow the story goes awry, and you can see this with the genetically modified foods and whatnot. So this is not necessarily genetically modified, but it allows for some advanced techniques. And so as part of that center and program, we have actually a program where every research group or thrust has in it partnered social science partner. And actually ethics is actually baked in as part of that process. And in order to if this is awarded, in order to get some of those annual awards, you would have to show what are you doing, not just for the science, the merit, and the broader impact, but also the ethics as well. I should say diversity is part of those annual proposals as well. So how are you broadening participation?
So that's really interesting. So the application I had in mind was basically related to Richard Dudley's question about Africa. So there are things going on in Africa now where they're switching from forests to growing monoculture, and also there are things where land is being taken back by the governments from the traditional people who farmed it and selling it or leasing it to big companies. And it seems to me what you're talking about in some sense definitely relates to that. And I'm just curious, is that part of what you just mentioned about this NSF thing? I mean, how broadly do you look at things?
NSF is more American centric, actually. We do actually have people like Mike Gore that does a lot with international agriculture, and actually he works in Tanzania and whatnot. He's done a lot to change from the starchy part of the maize to then have vitamin A in it, because a lot of people are very vitamin A deficient. So that actually is a part, but it's not as explicit, because it's NSF. But we have quite a few people that have projections into that. I myself separately have an outreach initiative to Ghana and South Africa, where we teach computing skills. And that's where first time I've opened my eyes to that. Like I went to a computer lab, people donated computers, but there was no electricity. That was so there's challenges there that I think in a first world like in the United States that people don't imagine. And I would like to start to apply this more. And some of what we like to do is take some of this underlying technology to some of these outreach programs that I have. We have a week-long, essentially hackathon, if you will, in some of those countries. So if we can tie a little bit more into digital agriculture. But that's a long way of saying that this proposal doesn't deal with that explicitly in Africa. But we do have some projection on it.
Well, I think you're a good start there. It seems to me this is some really interesting problems or questions about how you avoid race to the bottom, where basically most of the people get very poor because the technology sort of forces and enables Uber type of arrangements, whereas a lot of other people get very rich. And that's the kind of the ethical thing that I think is very interesting. And Cornell's in a good position to look into that, but I don't. We're organized in that way yet.
Cornell as an institution is, they say, what's it, agriculture to the world. We have some of the most, receive the most Gates Foundation money. We have hundreds of millions of dollars. And we care as an institution very much about it. And I personally have led a workshop that was called Satiate. Essentially, it was agriculture in troubled environments. And so and in some sense, this is my first foray into really not just making technology better for technology's sake, but how do you actually couple that with people and the ethics like what you're saying? So it's not a race to the bottom, but we do actually have technology that empowers people. Now, you may say that's idealistic, but I'm okay with that. We should start there as opposed to not starting there. Yeah.
So any other questions? I have one more, but I want to make sure other people get a chance to ask questions.
I had a question, Professor.
Please.
The question was about like actuators on a farm. So there were some really good examples about irrigation and like the fungicide and that sort of thing. What other actuators do you think would interface well with this type of infrastructure?
Yeah, essentially. I mean, the drones themselves and the robots are both sensors and
dropping
actuators.
Fertilizer, that sort of thing, or?
They, I mean, potentially they could. I mean, they could apply something that's very precise. There's also tractors that are autonomous as well. So at the same time that they are sensors, they could actually be used to apply a remedy, fertilizer, something. I haven't looked into that specifically, but I have seen and talked to some companies that provide that capability.
Awesome, thanks. And have you looked into greenhouses? And because there's, I think, a wealth of data there, and I know there's some stuff going on in other research labs, but this seems like good. A lot of work has been done doing the heavy lift with networking and that sort of thing.
I haven't done that yet. We have this deployment now, so as we get into winter, we may want to move into a greenhouse. I know Neil Mattinson does a lot with greenhouse, or I would say controlled environment agriculture. We also work. What's that?
Neil Mattinson's my boss. I work for him.
Yeah. So he's part of Cornell Institute for Digital Agriculture. We have a hackathon. One of the challenge areas is controlled environment engineering. And then there's a company, Plenty, that we worked with. Actually, I don't think Neil likes a lot of those companies. He doesn't think that they're scalable. They consume a lot of energy. But
he likes Plenty because there's a researcher that came from a project we worked on, Tessa, that works there. So I think Plenty is in good books.
Okay. Good. I know. Did you want to ask that last question, Al?
Yeah. My question is more away from the ethics part of it, but you have a lot of complicated systems. You're putting the systems of systems, and you're putting together. And I was curious what tools you're doing. There was the alternative to way of developing them is evolutionary. You try things and you gradually fix each part of it. Now, are you looking at it from a top-down way as well, where you try to compare designs before you try them out in the field?
Yeah, so a couple things there. We have like a apartment deployment, so we try and deploy this to the PhD students apartments right now. We also have been working a lot with Microsoft, so we're not starting from zero. They've actually done a lot of this. They are a for-profit company, and so they end up closing off some of this, where we're trying to make sure it gets added to the body of knowledge and whatnot. But we are able to use a lot of their systems and whatnot. And we actually have a very close collaboration with them. And then we're able to take that and extend. So in some sense, it's kind of evolutionary, but we have a pretty solid base to start from.
Thank you. So any last questions? We're just pretty much out of time here. Anyhow, I want to thank you very much. It was really a fascinating talk, and it's really on the frontiers of all kinds of really fascinating things. So I think it's great.
Yeah, thank you.
Okay.
Thank everybody. I appreciate it.
Okay. Bye-bye all.
Bye. Have a good weekend. Bye now.
Yes.
Thank you.